Good day and welcome to part one of our discussion on evaluating trigonometric integrals. The goal of this section is to come up with a method that allows us to integrate products that involve sine and cosine raised to powers and tangents and secants raised to powers. For the first part of this discussion, we are going to focus in on the first type of integral, that is integrating functions of the form sine to a power, cosine to a power. So let's begin with maybe the simplest non-trivial case. Integrating a single sine or a single cosine raised to the first power is no problem whatsoever. We've been doing that since Calculus 1. So the next possible case of interest would be integrating a single sine or cosine raised to the second power. And it turns out that this is something we can evaluate if we recall the correct trig identity from pre-calc. So to the side, let me note a few trig identities of interest that we need to make sure we are familiar with. So these are oftentimes referred to as the half-angle formulas. Sine squared x can be written as 1/2 the quantity 1 minus cosine 2x. And similarly, cosine squared x is 1/2 the quantity 1 plus cosine 2x. And note that these formulas are nearly identical, the difference being whether we have a negative sign or a positive sign. My somewhat silly way of remembering this is we have the cosine 2x. And if it's cosine squared x, the plus is telling us they are the same. If it's the sine squared x, the negative is telling us they're different. So if we go ahead and use this half-angle formula, or you may also recall it as being the double angle formula for cosine, we can rewrite our integrand sine squared in a way that makes it more conducive to integrate. So in this case, we are going to rewrite sine squared equivalently as 1/2 the quantity 1 minus cosine 2x. And when we do that, it's convenient to pull the constant 1/2 out of the integral, and what we are left integrating is 1 minus cosine 2x. And note, individually, each of these functions is extremely reasonable to integrate. Let me give one more reminder to the right. If you want to integrate cosine to the kx, where k is any non-zero constant, this formula you may recognize from using it is 1 over k sine of kx. You could check this by differentiating if you are unsure, and note also you could do the substitution u equals kx to quickly verify it directly. Utilizing this formula, when we anti-differentiate term by term, we would have the antiderivative of 1 is x, and then minus 1 over 2 sine of 2x. And this is a definite integral, so by the fundamental theorem of calculus, we evaluate from 0 to pi. So replace each x with a pi, minus sign, replace each x with a 0. And note, almost everything in sight here vanishes. In fact, the only non-zero term is when the 1/2 hits the pi. Sine of 2 pi is 0, sine of 0 is 0. So what we are left with in this case is simply pi over 2. And note this technique for integrating sine squared, that is rewriting it in terms of the appropriate identity, could be applied to sine squared or cosine squared. It could be a definite integral or an indefinite integral. That leads to our next case of interest. For these integrals of the form sine to a power, cosine to a power, if we stick to just a single sine or cosine term, the next case of interest would be cubed. So let's see if we can come up with an approach for anti-differentiating cosine cubed. And this is one of those scenarios where it's not easy necessarily to come up with the technique, but when we see the approach, it's extremely reasonable, and it's one we'll be able to modify to fit some other scenarios. So our goal is going to be to algebraically manipulate the cosine cubed, our integrand, using trig identities to assist us so that we can evaluate this with a substitution. So to start, I'm going to write this as cosine squared times cosine. And this is the key bit of intuition. I'm pulling off a single cosine from this odd power, and what I would like to do is have this cosine x dx play the role of du. So let's try to reverse engineer this a bit. If we want our du to be cosine x dx, I want you to pause your video for a moment and tell me, what should u be? Yeah, in order for du to be cosine x dx, we need u to be sine. So the question becomes, is there some way we can rewrite cosine squared so that it only involves sines? And this is where the Pythagorean identity comes into play. So adding maybe one more familiar formula to the right, cosine squared plus sine squared is equal to 1. So if we focus in on the cosine squared and isolate it, cosine squared is 1 minus sine squared by the Pythagorean identity. So rewriting this, we are now in a position where we can apply the desired substitution. So note the key technique. We had an odd power of cosine, so we pulled one of the cosines away with the goal of making it our du. The remaining even power of cosine we've rewritten in terms of sines using the Pythagorean identity. And now our integrand is much more reasonable. Applying our substitution, we simply have 1 minus u squared du. When we get an antiderivative into all powers of the variable, that is the ideal scenario. So anti-differentiating term by term, we now have u minus 1/3 u cubed plus c. So now, as long as we resubstitute, we are finished up. So sine minus 1/3 sine cubed plus c. And once again, to just reiterate, because this is a technique we are going to reuse, for the odd power of cosine, we pull off one cosine to play the role of our du, we rewrite the remaining even power in terms of sines, and we perform a u substitution. So let's move on to the case where we have cosines and sines involved and see if we can mimic this approach. So for our next example involving sines and cosines, let's investigate sine cubed times cosine squared. And I'm going to try to just follow the template we have in the previous example. An odd power of sine, let's see if we can pull off one of those powers and save it for a du and rewrite the remaining powers of sine in terms of cosine. So rewriting this, we'll have a sine squared sine x, which is just rewriting sine cubed equivalently, and then that cosine squared, which is still around. Our goal is to make this sine x dx du. And note, if we want du to be sine x dx, that would require u to be cosine. And note, this is not quite correct as I've written it, right? If u is cosine, du would of course have to involve a minus sign. So it turns out that this sine x dx might actually have to be minus du. But let's first see if we can make this work. So if we're going to let u be cosine, we somehow need to take this sine squared and write it solely in terms of cosines. So if we go back to our familiar Pythagorean identity, sine squared plus cosine squared is equal to 1. Isolating the sine squared, it's simply 1 minus cosine squared. And replacing that sine squared in our integrand, we now have something much more manageable. 1 minus cosine squared times cosine squared sine x. And we can now immediately rewrite our integral so it only involves our new variable u. So each cosine becomes a u, 1 minus u squared, u squared. And remember, sine x dx is minus du. A minus sign gets pulled out front, and we have the du. Now we're good to go. This becomes a much more familiar problem. And in order to integrate, we of course want to simplify a bit. And I'm going to go ahead and just do two things at once here for convenience. We'll take the u squared, we'll distribute it through. Simultaneously, we'll go ahead and throw that minus into each term as well. So we would have u squared times u squared for u to the fourth, and then we're subtracting away 1 times u squared. Anti-differentiating term by term, we have 1/5 u to the fifth minus 1/3 u cubed. And finally, we resubstitute. Each and every u needs to become a cosine. Now note, we have a few more terms in our integrand. We have a sine cubed and a cosine squared. But that doesn't change our approach. Because of this odd power of sine, we saved one sine to play the role of our du. In the remaining even power, we are able to rewrite with the Pythagorean identity. Once you make your substitution, you're left with a very reasonable integral that we are able to evaluate. And from the build-up, you probably have a sneaking suspicion that this same technique or strategy can be applied whenever there is an odd power of sine or an odd power of cosine. And I've included a few details summarizing this up. And to be honest, I always hesitate a bit to include the details because I don't want you to think there's something that needs to be memorized. That is not the case at all. It's all about understanding the strategy. If the power of cosine is odd or the power of sine is odd, regardless, the approach is going to be the same. So let me just explain the first bullet here, and I know notationally it might look a bit rough at first, but if we have an odd power of cosine, where an odd number is typically expressed mathematically as an even number, 2 times something, plus 1. So if we are in this scenario, we can rewrite cosine to the 2k plus 1 as being cosine to the 2k. Then we have the extra cosine that we're pulling off to play the role of our du. So note, even though it looks like there's a lot going on, the general technique, if it's an odd power of cosine, you pull off one of those cosines to play the role of du. Once you do that, you have some remaining even number of cosines, which means you can use the Pythagorean identity to rewrite that cosine squared as 1 minus sine squared. When you do so, you can always use the substitution u equals sine of x. And intuitively, the same idea as we saw in our above example works when you have an odd power of sine. So remember, there's nothing to memorize, it's just understanding the approach. Now there's another possibility. One of these powers is odd, or they are both even. And that brings us to our third bullet. If both the powers of sine and cosine are even, then we need to use these half-angle identities that we mentioned in our first example, and along the way, the Pythagorean identity as well. So we'll throw in there the fact that cosine squared plus sine squared is 1. And this completes our current discussion on integrating powers of sine and cosine. Where we will go from here in the next video is begin discussing powers of tangent and secant, and then a few videos from now we'll wrap up our discussion by going back and looking at some more special cases specifically related to the even powers of sine and cosine. And if you look ahead in your note packet, you'll see on pages 3 and 4, there are problems numbered 1 through 5. Typically, if we were meeting face-to-face, I would be finishing up our discussion for the day. And then when we met the next class period, I would be turning the floor over to you to work in groups on completing those 5 problems. So as usual, I'm going to make the request, before you view the next video, go to that 3rd page of your note packet and see what you can get done with problems 1 and 2. And note, if you understand the technique that we've applied here, the hints in those problems should allow you to modify the approach for powers of tangent and secant. So stay tuned and take care.